Okay, this is linking quite well over the previous one, previous talk. So, but it's going to be a little bit more specific, looking to link specifically changes in gene expression to regulatory elements like around the genes. Of course, we've seen this a lot now. SALMONIDs having a whole genome duplication, and it's been shown that the duplicates, a lot of them have been shown to be like conserved and conserved with with the pike outgroup, but we see also a lot of like divergence in one of the SALMONID copies. And it's a long-standing hypothesis that the whole genome duplications provide extra material, which allow one of the genes to be played with and diverge and have a novel function. And we can see that with changes in gene expression. But how does the gene expression change? And a very simple idea can just be, well, changes in regulatory elements around. But is that the case? That hasn't been shown yet. With this regulatory data, we can begin to explore such hypothesis and see if that is actually the case. Does changes in the regulatory landscape around genes after duplication changes the gene expression? All right, so we've got the ancestral gene, the duplication, and is there changes here? So we can first measure to see if there's changes in gene expression. We can compare between copies within the same species, copy 1 and copy 2, and for the second species. And we can also compare across species the same copy. And this analysis that we did here, so we got the RNA-seq data from the body map, and we looked here to compute the correlation of gene expression across these tissues to measure our similarity, and then look to classify analogs into ones that are conserved, so high correlation across all 4 copies, and the ones that are diverged, meaning that copy 1 in both species is different to its reciprocal copy 2. So they're not correlated. And so here is some distributions of Pearson correlation between copies 1 and 2. So within the same fish, copy 1 and copy 2, and then this is just a distribution of correlation, and then in Atlantic salmon and rainbow trout, and then across species, copy 1 versus copy 1 across the species. And we can see that a lot of genes, a lot of duplicates are highly conserved, and then we have also a proportion that is not highly conserved or correlated across tissues. And so we can put some filtering criteria to pull out the most conserved and most diverged analogs. And so for our conserved analogs, they needed to be correlated across copy 1 and copy 2 in both species, but also we want the conserved across species as well. But we have a slightly lesser threshold for that. And then for the diverged analogs, they just had to be different between copy 1 and copy 2, but they could be different in different ways between the species. So that's why we don't have the cross-species constraint there. Also to try and keep these numbers a bit proportional to each other as much as we can for statistics. Yeah. All right, and then this is just looking at those genes, the conserved analogs, about 3,000, and diverged analogs, about 1.3 thousand. Looking at heat maps of gene expression across tissues. So these are tissues, and then these are heat maps. The rows, one row is the same 4 analogs across the species and copies. And then if we cluster it, this is clustered by this gene. Then, yeah, conserved analogs, they look like they're expressed very similar across all the tissues. Most conserved are in brain. This is the Pearson correlation. More white means more highly correlated. And yeah, so more correlated between copies 1 and copies 2 in salmon and trout. Yep, and then these are the diverged ones, which have very low Pearson correlation. If you order it by here, you see that its copy here does not look like it, not correlated. Yep. So, do these changes in gene expression, do we see changes in gene regulation through enhancers of these genes? So we tried to do there's a lot of different ways that you could go about doing this, and I think it can get complicated very quickly. We tried to do a methodic approach. So this is going through the approach in order to compare enhancers across duplicates. So we have copy 1, copy 2. First we get these windows, and we use the same method that Camille did in her paper here, when she looked at comparing promoters and enhancers across mammalian species. Basically, you define in windows around the TSS of genes, right, with some overlap allowed and some conserved non-overlap allowed windows up to limits. So those define the windows for the duplicates. Then we took attack-seek robust open chromatin regions. So this is also attack peaks that are reproducible, so in multiple replicates. There, and we can then put those into our windows. And then we can annotate these using the chromatin states that overlap with this, as we've seen before. And with what in this analysis, we're mainly concerned with enhancer elements, the difference in enhancer elements, and I'm taking any kind of enhancers, either it's active or primed or poised, that we have different kinds based on the different various signals. Any one of these, it's labeled as enhancer for this analysis. And then we use the genome alignments that was described before. That gives us syntenic alignments across duplicates. And so we have these defined regions that we know are aligned between copy 1 and copy 2. And the results I'm going to show are going to be based on Atlantic salmon, not on rainbow trout. Atlantic salmon, we have more we have some more samples, we have some better data from more tissue samples. Yeah, so we're a bit more confident we have a bit more statistics to work with. So we're going to have a look at some of the results from within salmon. So just copy 1 and copy 2 of salmon. Yep. And so we're going to use basically like this data to compare regulatory element conservation. So and relate it to duplicates that are conserved in gene expression or diverged in gene expression. All right, so first is a conservation of enhancers across duplicates. Now this is looking at a difference can classify enhancers as a non-conserved, so whether it's just present in or just active enhancer in one copy, but in the aligned region in copy 2, it does not have an active enhancer. And an active enhancer in this case is going to be, we're going to be not so strict here. If it has enhancer activity in any tissue or stage, so like 86 or level of maturity or tissue, in any of our samples, if it's an enhancer, it's going to be labeled as it's an enhancer. All right, and if we have an active enhancer in both copy 1 and the aligned region in copy 2, then this is our conserved enhancer. Now, this doesn't happen very often. If we look at across all the enhancers, so not on, across all the lined up enhancers, about 6%. Let's see, first of all, we have two categories here, conserved, diverged. This is duplicates that are conserved in gene expression and those that are diverged in gene expression. And so if we look at the ones that are conserved in gene expression, about 6% of enhancers belonging to all of those duplicates are conserved, and then about 5% are diverged. Now, this is not too big of a difference, but it is quite significant because of just how many enhancers there are. But it's not such a big value overall, so most enhancers that you find within the genome are not going to be conserved across duplicates. But if we plot this, it seems to be missing color somehow. But if we do a QQ plot where we rank the values from lowest to highest, and we plot the values of the duplicates that are conserved, then, and then we plot the values. Oh, let's see. So this is on like a total level, and then this is looking at the proportion of conserved enhancers to non-conserved enhancers per duplicate pair. So this over this. And then if we look at the conserved and diverged, we can see that the conserved ones generally have higher proportion of conserved enhancers than the diverged genes. Yep, with a small significance level of the difference in distributions. Okay, so this seems like to be quite promising that and seems to make sense to say that the ones with more conserved expression have more conserved enhancers around their genes. But that was looking basically being agnostic of where the activity was. So is there conservation of enhancer activity like across our different tissues? So per conserved enhancer, we can now look at the activity across the different conditions. We have 16 conditions, 4 tissues, 2 sexes, 2 maturity stages, and then we can then have a look at whether there is activity in both copies, or so for this, is there activity in this condition? Is there activity in this condition, this condition, this condition? So this is the 16 conditions, and then we can label them if it's active or inactive in that condition, and then see when it's the same, or when they're both off, or when it's only active in one. And this, we can put this as binary, and then compute a Jacquard distance. And then this is Jacquard distance per enhancer, so per gene, we can either look at the mean enhancer distance, or the minimum enhancer distance. I think both are kind of interesting to look at the differences between enhancer activity duplicates. All right, and so we're going to be plotting again, somehow there isn't some color here, but anyway. Again, the conserved duplicates against the diverged ones. And if we look at the mean enhancer Jacquard distance per gene, so distance of 1 means it's the most distant, so this means more distant, and we see the values for the diverged, if we rank them up against each other, are overall more. So the diverged duplicates are less similar in enhancer activity. This is for mean enhancer activity. If we look at the minimum enhancer activity, then we see like even a bit more clearer that like when you have, let's see, that you will have a lot of genes that have like very high, very low Jacquard distance, so high similarity when the diverged ones are starting to get more and more distant. Yep, so basically up here means the diverged ones are less similar in tissue activity. This makes sense given what we saw before. But, yep, 1 minute? Okay. But there was a lot of non-conserved enhancers, so our last question was like, is there like maybe overall conservation of activity, so that maybe the enhancers are not lined up together, but they all work in the same way anyway, by being active in the same tissues. So we tried to have a look at the per condition. We looked at the proportion of active enhancers versus inactive enhancers around the genes, and we tried to look at the similarity of these proportions, and so this is basically removing the alignment aspect, but just looking at the proportion of activity of enhancers around genes within condition. Yeah, and then we computed Jensen-Shannon distance between these proportions, and then we could have a look at those of the ones in conserved enhancers, which we expect to be quite high, and then the non-conserved enhancers. And yes, the conserved enhancers are very high, so if they're conserved, then they're also, let's see, then the diverged duplicates have a high distance, so they're more, less similar. But we're more interested in these non-conserved enhancer elements around genes. So is there still like conservation of activity of these non-conserved enhancers? And so basically the diverged genes do have less, are more diverged in these, so less similar. So let's see. So conserved genes have more similar expression pattern of non-conserved enhancers, but it's not that great. I mean, the p-value is not too low. So I don't know if we can say too much about the non-conserved enhancers, whether they are still contributing to conserving gene expression. So this is the takeaway. Our conserved duplicates, they have more conserved enhancers that are aligned and active. They have more similar enhancer activity across conditions, and more similar enhancer activity across conditions for conserved enhancers, but maybe not for non-conserved enhancers. It's not too significant. So I think it's fair to say that we can see, which makes a lot of sense in the beginning anyway, that changes in gene expression is linked to changes in regulatory elements. But even though that could make a lot of sense, we have not seen really it so far without this type of data. But this is like a very sort of high level look, because there's so many other factors that come into play, like how much does this affect, what genes does this affect, in what conditions, which elements matter, because there's a lot of different regulatory elements around the genes, or maybe only a few conserved ones matter, and other functional genomic effects like the organization of the chromatin, or other non-coding elements around the enhancers that affect gene expression. Yeah, together it's all very complicated, but there's at least some signal between this, which is a good sanity check for the data. Yep, and some novel needed information for looking to see how duplicates have evolved. Okay, thank you.